This is an explanatory video for lab 3. We will compute the well-known mathematical constant pi. If you are not familiar with pi, then it is simply the ratio of the circumference and the diameter of a circle. So if you denote the circumference of a circle by p and the diameter of the circle by d, then p by d equal to pi. This is one of the most amazing constants in whole of mathematics, and it appears in many places. I am sure you have encountered pi in many different contexts in your high school mathematics or right now at the university. One of the things that we'll use is we'll use some notion or some concepts of calculus, in particular integral calculus, for computing pi. Now pi is a constant, but in a digital computer, if you have to use pi, you have to use a floating point number or a double precision number, so something like 3.14, etc. In fact, it is well known that the decimal expansion of pi never recurs. In other words, it is an infinite decimal expansion. So in many engineering applications, it's very important to have a very accurate value for pi when you are using pi as a constant in your calculations. And in this lab, we'll learn how to calculate pi very precisely. And we'll use our parallelizing concepts using OpenMP for doing that. However, before I do that, I have to explain to you how pi can be computed by writing a program, and even before that I have to show you an integration that gives pi as the result of the integration. Now if you are not familiar with calculus, you need not worry, because the knowledge of calculus will be helpful in appreciating it. However, if you don't know calculus or you have forgotten calculus, then it's not a problem at all. You will be still able to write the program. Now, most numerical computing algorithms that we implement on computers are basically based on calculus, and they implement the computations that we do in calculus, like differentiation or integration, in a numerical way. That is, in a step-by-step fashion. In particular, for today's lab or this week's lab, what we need is we need to evaluate this integral. So 4 over 1 plus x square dx. Now this will give us pi if we integrate this. How to complete the integration? I'll show you that. However, that doesn't have any direct relevance to the program that we'll write, except for a better understanding of what is going on. So usually what is done is this integration can be evaluated by so-called method of substitution. So you can assume x equal to tan theta. In other words, theta equal to tan inverse x. I'll not go and explain all of this, because either you know it already or you don't know, and don't worry if you don't know. So if x equal to tan theta, then dx will be sec square theta d theta. Now substitute here in this expression the indefinite integral. You will have 4 dx will become now 4 sec square theta d theta, and in the denominator it will be 1 plus tan square theta, and 1 plus tan square theta is sec square theta. So this and this cancel out. Sorry, not the whole thing, but only this part. So because 1 plus tan square theta equal to sec square theta. So this cancels out, and what you are, I'll now put back the limits. What you are left with 0 to 1. I can take out the 4 outside the integral sign, d theta. In other words, I have this integral and the limits 0 to 1. Now we know from here that theta equal to tan inverse x, so I'll write that for tan inverse 1 minus tan inverse 0. This is the way usually definite integrals are evaluated, and tan inverse 1 is nothing but pi by 4 because tan pi by 4 is 1, and tan inverse 0 is nothing but 0. So this thing, this 4 and this 4 cancels, and you have got pi. So in other words, if we can somehow implement this integration in the computer by writing a program, we'll get the value of pi. Now, how to do that? We have to take another view of integration where integration can be viewed as a summation. So if I draw the picture of that integral which I wrote earlier, remember there is a 4 here, 1 plus x squared. 1 plus x squared, if you see when x equal to 0, this is nothing but 1. And when x equal to 1, this is nothing but half. And similarly, when x equal to minus 1, this is also half. So this thing, I am evaluating this thing, 1 plus x squared. So if I plot now 1 plus x squared along this axis and x along this axis, then what I get, we are interested, remember the limit that we had is 0 to 1. So this is 0 and this is 1. So we are interested in how it looks between 0 and 1. So when it is 0, the 1 plus x square evaluates to 1, and if you multiply by this 4, you have 4 here. So this is 4. And when it is 1, 1 plus x square evaluates to half, just like here. So if I draw 3, 2, 1, and let us say this is half. So the graph will look like something like this. So if you have done calculus and if you remember, basically to evaluate this integral is equivalent to